due to day today. Oh, and before I forget, Monday is a holiday, so there will be no classes on Monday. So bear that in mind. So I guess you can have a long lie-in on Monday. Okay. Well, let's look at what we've covered yesterday. If you want to find the volumes of revolution, that's what we call it. If it's a single curve, like y equals x squared or something, and you're rotating about the x-axis, the formula is this integral. If it's the area between two curves, like y equals x and y equals x cubed, then it's this formula. And you have to remember that one of these should always be first, and it shouldn't be the highest up of the two curves, and this should be the lower down. So the big curve, take away the little. Now, if you rotate the picture and do it rotating about the y-axis, going like this, it's essentially the same formula, isn't it? It's just pi and the function in terms of y squared dy. And if it's two curves, it's the same thing. But when it's two curves, you have to make sure you get these two guys the right way around. And isn't the rule the guy furthest to the right goes first and the other one goes second? Seems familiar? We've done examples of, I think, every single one of those combinations. So what is left? Well, what is left is this guy, and this is why it gets kind of busy. How do you find the volume of revolution when the axis of rotation isn't the x-axis, right? Your horizontal axis, but a line that's parallel to it, like a line like y equals 2, or y equals 4, or y equals -2, right? That's the new puzzle. How do you do that? Well, the generic formula for a single curve, which is ones we're going to do right now, is the integral from a to b pi something squared. Now, that used to be just f of x squared, but that's going to have to be adapted because we're not going to be rotating about the x-axis anymore. We're going to be rotating instead about an axis that's parallel to the x-axis. So let's show you what one of those questions might look like. We're being asked to find the volume of revolution for, oops, I will do that one, but that's not the one I intended to do first. Let's find, oh dear, it's hard to find one when you really want one. Okay, this one is like question 10 from the homework. It's y equals 1 plus secant x, so that's your formula. You've been asked to do it from pi upon 3 to negative pi upon 3. Also, you're going to use the line y equals 4. No, I will do that one as well. That one is a double one. And the other one that I didn't do is rotating about the y-axis. So I need an x-axis question. Maybe I can find one from the homework. So I want something with a y equals, and I want one curve to do it to. That's a double curve, so I can't use you. That's a double curve, can't use you. Another double curve. It's a y-axis. Yeah, it's a double curve. Another double curve. Oh, okay. Evidently, none of your homework questions are this, so I can create one then. Here goes. Let's do y equals x squared. Looks like this. Let's have it from 0 to 2. So this is going to be the area that that we're going to rotate. I'm just going to go for it. Here we go. Tell me a horizontal line that you'd like me to rotate this shape along.
3.
So y equals 5. You can't pick anything inside the shape. They don't work. You can even pick some negative ones if you really felt like it. But probably not choose that if you're sensible. The numbers are horrible. Give me a line to rotate.
6.
8. Right, where do you want me to rotate it? 4, 5, 6?
8.
8. Well, I'm going to pretend that that's 8. And here is the axis of rotation. And have you noticed that that horizontal line has the equation y equals 8? Even although it's parallel to the x-axis, its formula has a y in it, right? So you're going to rotate about this guy. So the formula you're going to use is this fella here. It's going to be the integral from a to b pi, a guy that I'm calling the big radius squared, take away a guy I'm going to call small radius squared dx. So you got your picture, and if you don't have one, you really need to draw one. We're going to take this shape and we are going to look at it, and we're going to essentially cut it this way. So imagine this little rectangle here. That's basically just there so I can put in positions. The distance from the axis of rotation to the top, and then you have the distance to the bottom. Now, when you do that, won't one of these be small and the other will be big? It's kind of obvious. And isn't this one the big one? So the guy I'm calling the big radius, and this one here next to it, I'm going to call the small radius. And the reason we call them radius, if you can imagine cutting this shape and rotating about that, wouldn't you see a donut shape? A little circle and then a bigger one. So that's why I'm calling them big radius and small radius. Now, this is your generic formula. This is going to be the one you're going to use. So you're going to go here and you're going to say, okay, start at 0, finish at 2. Stick the pi outside. Now, big guy squared, take a little guy squared. Let's see what he looks like. This distance here, from here to here, is the big radius. Won't it be the same number no matter where I do that little red rectangle? So the big radius is, in this case, a fixed number. It's 8. Now the small radius, that's going to be a little bit more tricky to get. The total distance from here to here is 8. The distance from here to here, right? Or sorry, the distance from here to here first, isn't that the value of f of x? So what's the small radius going to be? Well, it's going to be 8 take away the f of x. That means it's going to be 8 take away x squared. So we now have an 8 take away an x squared squared dx. If you can get that bit right, you've basically broken the back of the question, because from this point onwards, it's just normal algebra and integration. But creating the structure that you need to put together to get the volume, that's where it's going to get tricky. So let's take it a little bit further. going to be the integral from 0 to 2, 64, take away 64 minus 16x squared plus x to the 4. And that's going to be the integral from 0 to 2 of 64, take away 64, add 16x squared, and subtract x to the 4. And you end up with and if you integrate that, you will be getting the volume of revolution of y equals x squared from 0 to 2 being rotated about the line y equals 8. So the whole structure I'm going to figure out is how to make this happen. And I think I already said that. This is going to be a tricky day, isn't it? This is not clear cut. You got to think hard. Well, that's with a single curve. So let's do one of the ones I'd planned to do now. Which one? So this one is question 9. No, this is question 10. My apologies. Y equals 1 plus secant x from x equals pi upon 3, negative pi upon 3. The line y equals 4. And we're going to rotate it about the line y equals 2. First things first, I need to do a sketch. You really have to visualize this. It's too difficult to try and figure out what the heck's going on inside just by using the information as it's written. So with a bit of luck, I'll have already set up Desmos, did I? Thought I had. Okay, hold on a second. Here we go. Right. I'm having, what do you call it, technical issues here. There we go. Are you now looking at Desmos? Are we good? Because I don't want to start talking and find out you're looking at some other thing. Is this Desmos in front of your screen?
Yes.
Yes. Yeah.
We are good to go then. Right, so the function that we're going to do is y equals 1. Well, this doesn't work really well. My keyboard is almost off the desk, which means it's probably going to fall any second now. So here we go, y equals 1 plus, I hope it recognizes secant. Should. There's secant x. Oh, it does. You see secant x? That's cool. And I'll hit enter. And the other line was y equals 4. So it looks like that. And you see it's this blue line here. Now all I'm going to do is just zoom in on the picture a little bit. There. So we are basically interested in this shape that's the intersection of those two. And that's from here to here probably, right? So can you imagine taking this shape here, right? And rotating about the line y equals 2, which would be here. So what I'm going to be drawing for a few seconds is pretty much what you see. So I put it in a Desmos and I figured out what the area that's going to be rotated is. And then I can imagine that the axis of rotation is this line called y equals 2. So now when I return, you'll be able to see my very crude example of that picture. So we are taking this shape that looks like a boat and we're going to rotate it about that line. So far, so good. Now, step 2 is the crucial one. Set up the integral. So we are going to be looking at the volume. It's going to be the integral from, well, I'll put the generic version in, from A to B, pi, big radius squared, take away the small radius squared, dx. Now the A and the B come from here. So that's going to be negative pi upon 3 to positive pi upon 3. I'll stick the pi out here. And now if I want to figure out who the big and who the little radius is, choose a vertical rectangle. This one here. And the distance from the axis rotation, that's the small radius. And the distance from the axis of rotation to the top line is the big radius. So the first guy you meet is the little radius. The next guy you meet, that distance is the big radius. Okay. Now be careful. Let's do the big radius first. What's the distance from this line to that line? Because that's essentially going to be the big radius.
2.
Agreed. It's not 4. Agreed. It's just like it was said. It's 2. Right? 4, 2, 2. So we have, whoops, we have 2 squared. Now the small one, which is this distance here. Do a little calculation for the small one. What do I know? Well, I know that the distance from the top to the bottom, right? That's from there to there. It's 4. And don't I know the distance from here to here, which is f of x? So won't it be 4 take away 1 plus secant x? And so the small one is 3 take away secant x. So that's subtract 3, I don't know I'm green now, take away secant x squared dx. So it's pi, the integral from pi upon 3, negative and positive, 4, take away 9 minus 6 secant x's plus a secant squared x dx. So that's pi, the integral from here to here. Oh God, that's messy, isn't it? Negative 5 plus 6 secant x plus secant squared x dx. And then you do step 3. Oops. Find the volume. Right. This particular one was big take away small squared. The big was 2, so I squared it. The small was 3 take away secant x, and I squared it. First guy take away second guy, you end up with this mess. At this point here, it really should just be integration. And this one's got a little kicker in the tail just to make life even more awkward than it already is. I can integrate negative 5. Would you agree that just gets you negative 5x? Can I integrate secant squared?
Yes.
What's the correct? What is the antiderivative of secant squared?
Tangent.
Right. Now there's a guy in the middle called 6 secant x, and you're going to occasionally come across this. in our standard table of antiderivatives, I don't have secant x. There are a lot of things I don't have there because there's so many things that could be there. We only put the major ones in that. Remember that table where we had the antiderivative of e to the x and 1 over x and secant squared and stuff like that. So when you come across one that's like this, all you have to do is go to the book and find out what the antiderivative of secant x is. And trust me, if I remember correctly, it's some really ugly thing, like the natural log of the secant plus tan x or something. Whatever it says, you write it down here, and you're finished. Right, so if you come across an integral and you're saying, I don't know what the square root of 1 minus, I don't know what the integral of the square root of 1 minus x squared is. You just go and find it. In the old textbook, they had a section, an appendix at the end of the textbook that just had every conceivable standard integral that you could ever come across, and you would just go there and look. So hopefully the ebook's got the same fella. I think it's living up to its expectation of being, this is going to be tough. Agreed? So let's, oh, any questions? Because there could well be in this.
I actually have a quick question.
Yes.
So when we're trying to find the small radius in this example, do we start, is it basically we starting from the first y and then plus the...
Yeah, you're trying to find that tiny little distance there. So when you're saying, do we start at the first y, I'm not sure what you mean. We start at this line and try and count how far it is to that guy. That's not
I think he
your
was talking about the first line because you plugged in 4 minus f of x.
Oh, well, you're talking about that, yeah. So if I wanted to get the big radius, I'm basically just trying to find that distance, either as a number or a number with x's, right? That's what I'm going to get. And if I look at this picture, I can see that this line is 4 and this line is 2. So I just said, okay, 4 take away 2. But if you notice that the other one is 4 take away the function. So isn't there a kind of the line take away something, the line take away something kind of pattern going on here? One was 4 take away 2 and the other was 4 take away the function. Is that more along the lines of the question?
Yeah, yeah.
Right. So if that was your observation, yes.
Okay.
That's kind of pattern that is going on there. Okay. Where shall I go next? Let's do a version of 11. You might get lucky in one of these versions because I know that WebAssign randomizes some of them. So I'm doing a 2 sin x one, but maybe the one that you'll end up doing is a 3 sin x or something. It won't be major difference. Darn it in space. There we go. Okay, step 1. Can you imagine that's 2 sin x? And can you imagine that's 2 cosine x? You could certainly do Desmos on that. Can you trust me that I already know that answer there is pi upon 4? You could probably predict it from here. So the piece that we are doing is this little piece here, isn't it? And we are rotating it about a line down here. So step 1 is draw a picture of the area that's being rotated, including the axis of rotation. Then we move into phase 2, which is the hardest part. It's going to be pi, the integral from a to b of pi, big radius, take away small radius squared. 0 to pi upon 4. Right, now, if you take I'll make it green. If you take your vertical rectangle, the distance from here to here, won't that be the small one? I want the distance from here to here, we'll call that the big radius. Are you happy about from the axis rotation to the first piece of the rectangle is your distance we call the small radius, and then from the axis rotation a little bit further on is going to be your big radius. So I guess I should maybe set up somewhere at the side what those two guys are. Okay. If you wanted to find the distance from here to here, wouldn't it be 1 plus the value of the function, which is 2 cosine x? So 1 plus 2 cosine x. Do you see in this case, it's 1 plus the function rather than a subtraction? So it does matter where the axis of rotation is. What will be the distance from here to here then? Well, won't it also be that distance 1 plus the value of the function? And can I fix this? There we go. The big one is this guy, so that's a cosine. The little one is the sine. So big radius, 1 plus 2 cosine squared. Small radius, 1 plus 2 sine x squared. So do you see in this case it was 1 plus a function, 1 plus the other function. In the previous case it was 4 take away a function, 4 take away a function. Do you see it is a consistent pattern, but each pattern depends on the orientation. You know, it means where are you rotating? Down here it's a 1 plus the function. See up here it would be 4 take away the function. Axis of rotation down here, 1 plus the functions. Axis of rotation up here, 4 take away the function. Because one you're pointing down the way and you're subtracting to get distances, and the other you're pointing up the way. Now, this fella here has to get FOILed out, so that's 1 plus 4 cosine x's plus 4 cos squared x's. Take away 1 plus 4 sine x plus 4 sine squared x's. One take away one gone, 4 take away that guy, 4 of these take away that guy. Let's see what it all looks like. It's going to be 4 cosine x's, take away 4 sine x's, plus 4 cos squared x's, take away 4 sine squared x's, dx. Well, we fought our way through well, but we still have one last issue. I need to be able to find antiderivatives of 4 cos squared take away 4 sine squared. Wouldn't it be much nicer if it had been 4 cos squared plus 4 sine squared? Because then can I just turn them into 4 and that wouldn't have been a big issue. So somewhere, someone in this class, hopefully, is going to tell me what cos squared minus sine squared is equal to, because it's a trig identity.
1.
That would be correct if there was a plus. But since it's a subtraction, and that's not going to work. So what would it be for this guy? It's a double angle formula.
Cosine 2 theta. Or
There you go. In this case, x, but you're bang right. So you're going to have to, I don't know how you're going to work this out. You're going to have a list of trig identities somewhere handy. Double angles especially, right? So once you know that that's them, won't 4 of them just give you 4 cosine 2x's? Now at this point, I'm going to have to move a little bit quicker. We know how to integrate 4 cosines, agreed? We know how to find the antiderivative of -4 sines. We can do that. How are you going to get the antiderivative of 4 cosine 2x's? Because the only reason we've done that is so we could find its antiderivative.
Use a
U
U
sub.
sub.
Substitution.
Could use, and the u sub would be 2x.
Mm-hmm.
Agreed?
means-
Right. So these are not short questions. You agree there's a lot of stuff in these questions just to get the answer. And you're going to have to find things like the exact value of sine and cosine of pi upon 4, right? Just to make things even more interesting. Are we good?
Professor,
Yes.
could you explain again how you figured out what the big and small radiuses were?
Sure. I'll try this picture again. Maybe do a bigger version of it. Where's my pens? Here are my pens. Right, so that's a kind of larger version of what's going on here. So if you're going to rotate about an axis like y equals -1, then you do a, I wish I'd put them there now. You do a rectangle. Just a general rectangle, technically anywhere you like. And the distance from here to here is the small radius. Are you happy about that distance being the small radius?
Yep.
Right. So I'm going to calculate what the distance from here to here is. And the way I'm going to calculate it is I'm going to notice that isn't the distance from here to here fixed? Isn't it 1? And you might say, why do I know it's 1? Well, isn't from the x-axis to the line y equals -1, 1 unit away? Its distance is 1. Isn't that distance from here to here 1? Isn't that distance from here to here 1? Isn't that distance here to here 1? So surely shouldn't that be 1? You're looking puzzled, I'm not sure.
I'm confused, but there's like an arrow above the x-axis. Like, what's that?
Yeah, well, it's coming up.
Oh,
Then I
okay.
find this piece. And won't those two added together be the whole thing? Right? So what I've done is I've taken the whole thing and I've broken it into 2 pieces. And then if I add the 2 pieces together, that will be the distance that I'm looking for, called the small radius. So,
Okay.
1. Now, the second piece of the puzzle is I also now need to find that little distance, because I know that bit's 1. If I add the red bit, I'm good. Well, isn't the distance to there, isn't that just the value of the function?
Mm-hmm.
And that's the 2 sine x. And that's where the small guy came from. Now, if you want to do the large guy, so basically I found this distance by finding 2 pieces and adding them up. Now, to get the large distance, I'm going to start off with the same idea. Isn't it 1 to here? right? That distance is 1. Now, how much is it to go from there right to the top? Well, it's that value of the function. The y value is this guy. So this ends up being the other half of the puzzle, the guy that goes there. And that's how I created them.
Okay, thank you.
You're welcome. Keep tracking time here. I think we've time for just 2 more. Let's get the next one. This is similar to question 7 in the homework. And this is y equals x squared, x equals y squared, and it's being rotated. They don't have a lot of imagination here. They keep on picking ones of various kinds. About the line y equals 1. So we are interested in rotating the area between those 2 curves about the line y equals 1. So what I'm setting up right now, you can't see it, but you will in a second, is these 2 guys. Okay, now ready to show you. Desmos is going to be really indispensable for these questions. Can you see I've got the blue curve and the red curve? I've got my picture. Right? I'm pointing at a screen, you can't see me point. Do you see this guy here is x equals y squared, and the red one is this guy? So the piece that I'm going to be rotating is this, I don't know, looks like a fish to me. So what I'm doing right now is trying to draw a little baby sketch of that same piece of information. And we're being asked to rotate this about the line y equals 1. If I put the line y equals 1 in, you should be able to see it. There it is. You see that green line? That green line is the axis of rotation. So now I'm going to return to the whiteboard. And we'll see how this works. Right, that's basically the same picture you saw a few moments ago. I do need to figure out what we're going to be doing. So it's going to be from A to B, pi, big guy squared, little guy squared, dx. Going to suck out the pi. There's my first issue, although it's not a big issue. Don't I need to know where there is and where there is? Agreed, I need to know. I think you could do that in your head. Anybody want to tell me what well, I'm telling you that one is 0. And what do you think that number is?
1.
Well, yeah. We comfortable about that? Now, I've got big and small, that's to come. But before I even do that, that's the format that these equations have to be written, because they have to be in terms of x. Do you see how this one is actually the wrong way around for us? So if I rearrange this, are you happy with it being equivalent to just saying y equals the square root of x? Can you see how you can come from this line to that line? I just basically take the square root of both sides. So we got a big and we got a small. We have to find out what the distances are. So I'm not sure what color I'm going to do now. I'm going to do red. Here is a random rectangle to get me started. So I'm looking at this distance here is going to be called the small distance, right? Does anybody Can anybody tell me, in terms of x, what the distance from the dotted line to this top curve is?
Would it be square root of x minus 1?
So it could also be that. So let's see which is more likely. Would you agree that the 1 is bigger because it's higher up, and that the square root of x is a little bit lower? So does that give you an idea of which of these would be the more realistic for a distance?
Yeah, it should be 1 minus the square root of x.
Agreed? Highest up, lower down. So we now have the small guy. He's 1 take away the square root of x all squared. Okay, the big one is from there to there. But actually, you kind of know what it's going to be, because don't they both have the same kind of look? So hopefully it's not a surprise that the big one is 1 take away x squared. And it's the same argument. If you start there and you're going there, you find the total distance, which is 1, and you take away that little guy, which is basically the x squared piece, and that gets you the piece that you want. So we have a 1 take away x squared squared dx. Because I'm running short of time here, FOIL that out, subtract the 2. For the most part, aren't you just going to be left with x cubes and x squareds and stuff like that? One exception, aren't you going to have some square roots of x's in here? In fact, I believe you're going to end up eventually with that. How are you going to integrate that?
Take it as x by the 1/2 power.
And then off you go, right? So that's just a minor hiccup. It's a lot less hiccup than cos squared minus sine squared was, right? That was a kind of major hiccup because that was a hard thing to deal with. But a square of x is pretty minor. You can deal with that pretty easily. Are we good? Right, so our last question is going to turn things on its head. I believe this is question like number 9. And we have y equals 8x cubed, y equals 0, x equals 0, and we're being asked to rotate about the line x equals 2. Now I could probably do this, and for speed I am, and without using Desmos. So can you trust me that that's what y equals 8x cubed looks like? Pretty obvious shape anyway. Now, where is y equals 0?
Directly on the y x-axis.
Directly on the x-axis, so it's that line there, right? And what's the other guy? X equals 0. Have I written that down correctly? Because that don't make sense to me. One of these should be a number. You want to hold off a second so I can check what that question really is. They can't both be 0. One of them has to be a number. Let's find out which one. Question 9. There we go. And it's x equals 1. So it was a number. I thought it had to be. Okay, so I just misread the question when I wrote it down. So y equals 0, x equals 1. Now, would you agree x equals 1 goes here? Y equals 0 goes here. So what they have just told us, with all of that, has told us it's this guy. Now, rotating about the line x equals 2. where is the line x equals 2 going to be in this picture?
To the right of x equals 1.
Yeah, so it's going to be about here somewhere. In fact, isn't this the one and only question where we get to rotate something parallel to the y-axis? So far, so good. Now, when you rotate things parallel to the x-axis going this way, isn't everything in terms of x, right? Y equals x squared, y equals sine x. When you rotate things parallel to the y-axis, shouldn't you have functions x equals function of y, right? X equals y squared, x equals y cubed. So I'm going to go straight into this fella here. I'll do it over here actually. And I'll figure out the form that he needs to be written. If you divide everybody by 8, you get that. And if you take the cube root of everybody, you get the cube root of that. And can I tell you that's the same thing as that? So this fella here is going to be x equals 1/2. One of them should be y. Why does that look more like an x? There we go. We gotcha. Right, formula for calculating it now. It's the integral from c to d. Once we figured that out, pi, big radius squared, small radius squared, dy. Would you agree the formula is virtually identical to the ones we've been using for rotation about parallel to the x-axis? But now things are in terms of y. So that means that the picture I've got is correct, but the picture I've got does not have the numbers I need. Don't I need to know where the y's start and where the y's finish? Because c and d are the y values. Right, you start at 0. And would you agree this number's 8? Can you just use that to figure out the value? So we're going to go from 0 to 8. Now I have a big radius squared, take away a small radius squared, dy. If I can figure out what these two things are in terms of y, we are done. So what direction do you think my little rectangle is now going to go based on the fact that we're rotating vertically? When we rotated horizontally, wasn't my little rectangle, that way, right? X-axis, rectangle at right angles. Can you see we should be doing a rectangle this way? So if I go here and I do my little rectangle this way, then this distance here to here is going to be the small radius. And this distance from here to here, that's what we call the big radius. Right, so it's left, right, rather than up, down. Okay. Let's do the small one. What's the distance from this dotted line to that vertical line?
1.
And it's 1 all the time, isn't it? 1. Now, to get this distance from here to here, this little fella in here is basically 1/2 the cube root of y. This distance from here to here is 2. This distance from here to here is 1/2 cube root of y. The guy we want, right, is that distance. Okay, what is that distance then using y's?
Two minus the function.
If you look back at some of the earlier questions, isn't it very similar to that? It's 2 add the function, 2 take away the function, that kind of looked at it. Okay. So next line, pi, the integral from 0 to 8. This guy, well, I'm going to rewrite this guy as a fractional power. I'm then going to FOIL them, and you're going to get 4. Eventually, you're going to get 2 of these guys, and you're going to get this guy times itself. That's going to be a quarter y to the 2/3 take away 1. So if you do this guy times itself, you will eventually get these 3 take away 1. That will become 3, 1/3, and 1/4. One of the reasons I turned the cube root guy into a fractional power, because there's really 2 reasons. One of the reasons is it's a little bit easier to FOIL things out because fractional powers times other fractional powers, you can figure out what they're going to get you. And the second reason is, isn't that going to be much easier to integrate? Okay, I want you to say hi, and that's all we have time for. ... So we got attendance. Good hunting. This section is, as I mentioned at the start, it's going to be tricky, right? You only get about, what, 5 examples. I think I've covered 4 of them, at least versions of 4 of them. So hopefully that's a good head start for you. And won't see you on Monday, so the next day I will see you is Tuesday. And that is us. Any questions?
Can we still stay for like?
Oh, of course,
help?
yes. Anybody who wants to hang around because they have some homework questions, I'm answering some questions at least for one student, so you might as well join them and you can have your question answered as well. Otherwise, see you Tuesday. Jocelyn, are you here or you just turn up and then disappear and I can't hear you? Jocelyn, I'm here. Okay, evidently she's not. Matthew, since you kind of got first dibs, we'll do your question first and then we'll just kind of rotate it around the others so that everybody gets a little shot. So which one do you want me to go over? Or what issue? Whatever. You're frozen, Matthew. Can you hear me? Okay, Douglas. Matthew, can you hear me?
Uh-huh.
Okay, so what was your question? I directed it to you first.
So it was question 1 on the volume somewhere.
Number 1, let's go for that straight away.
It was just like 2 parts, or one part, where it asked, where you had to enter in the inner and outer radius. I didn't know how to do those ones.
Okay, so I'll put it on the screen right now.
Everything else I knew how to do.
Cool. Right, so it's basically this question here, number 1.
Mm-hmm.
Okay, so you've got a y equals 3x, a y equals x squared, we are done. Find the volume of resultant solid. So the curve y equals 3, it intersects at the point 0, 0, which is pretty obvious, and it intersects at 3, 9. So you were cool with that, 0, 0, and 3, 9.
Mm-hmm.
Right, now, what you were saying, is it this bit here, inner radius and outer radius? Is that what was causing the issue?
Mm-hmm.
Right. The axis of rotation here is the x-axis, right? This line here.
Mm-hmm.
What they're calling the inner radius is the distance from the axis rotation to the first curve. So you imagine you were here to here, and that would be x squared. So that goes there. And then from here, going to the second guy, 3x, and that's what goes there. So the inner radius is the distance from here to here,
Mm-hmm.
the x-axis to the curve, and the outer radius. Think of it as small and big. That's the terms I've been using. So they're using inner radius where I would say small radius, and they're using the word outer radius when I would say big radius. Okay?
All right, thank you.
Anything else? Because that really
Or
doesn't...
should someone else go? Or
Well, that was such a quick question. I think you really deserve a full one. So what's your next one?
okay. So the other one was question 2. I didn't know how to do any of it.
Okay, so there is a lot going on in question 2. So give me a few moments to get this thing set up. So it's kind of distracting because I have the answers in front of me, but that's fine. So you got that picture to the left-hand side, and basically what you're trying to do in this story is find the area of that pink, I guess it's a square, that pink square, right?
Mm-hmm.
And so they say we place the origin O at the vertex, and it's a pyramid, must be a square base one, passes through the plane, right? Gotcha. Perpendicular, yeah. Right, we can express S. So this picture down here, if that's X, we can express this distance here by observing what's called similar triangles. Okay, so let me just draw that picture and show you what the heck's going on. So it goes a bit like this. Okay, now I'm going to leave out of this thing. Just mute it, get background sound. And we'll show you how they came about calculating the value of this thing here called S. So this is the picture they had at the bottom. The distance from here to here is X. This vertical distance is S. This distance from here to here is H. And this vertical distance here is called L. Now, there's a property called similar triangles, which says if you have two triangles which are essentially the same shape, but just one is, say, bigger than the other, in this case we do. In this particular triangle, the distance here is X, and this distance is S. So that's basically that shape. And then the whole thing has a distance H and a guy called L. And according to the properties of similar triangles, corresponding sides are in equal ratio, which basically means this. If you take X and divide it by H, it's going to be the same number as S divided by L. So far, so good. Now, if you do a little cross multiply, you get that. And if you then divide everybody by H, you get that. So if I now kind of return back to that question, the thing that I've just written down is that guy. So S is equal to this guy. Now, they told you that information up there. I don't know why they bothered to have it, because it's true even if you don't. And that's fine. Okay. Now, if you know S is this guy, won't S squared just be the square of this guy? So won't S squared be L squared, H squared, X squared?
Mm-hmm.
And isn't that the area of the square? Because if you know this side here, down here is S, and you know this side here is the same, then won't the area of this shape be S times S? This guy.
The area
Of that pink
okay.
cross-section thing, right? Now, if you find the integral of that pink thing, AX, starting at the beginning, which is 0, and finishing at the end of the shape, which is H, you have now got the formula for the volume. It's the integral from 0 to H of this guy. Now, they've given you that. So all you need to do is power roll. Now, think of L and H and L squared and H squared as well as just constants. So can you see what happened here is that the square got 1 power added, divided by 3, but the other two guys are still there.
Mm-hmm.
Right, if I said 4x squared, wouldn't it be 4/3 x cubed?
Mm-hmm.
Add 1 to the power, divide by the power. Okay, it's not 4, it's a funny thing called L squared over H squared, but it's treated just like it was a 4. It's treated as a constant. So the antiderivative of this guy is this fella here in the box.
Mm-hmm.
And then you plug in x equals h, and then you plug in x equals 0, and then you tidy up by cancelling some h's, and you would end up with this answer here.
Okay, so basically we're finding the area of that, like, of that, like, square.
Yeah, and using
then,
that to get the volume of the shape.
Okay.
Because there's a formula that says the volume of a shape is the integral of its cross-section function, dx.
Okay.
Most of the questions we've been doing, the cross-section has been circles, so that's why it's pi r squared. But basically, that's just AX is the area of a cross-section. So in a circle, pi r squared is what we typically are using. But this is not a rotation shape. This is a different kind of solid, and therefore the more generic version of the formula is that the volume is the integral from the start value of x to the finish of a random vertical cross-section of that shape. So you cut it and you get the area of that pink guy. In this case, he's called AX. Then you just need to integrate that and you've got the volume of the entire shape.
Sorry, the audio just cut off for me.
At what point?
You were saying that the shape is different from the ones we've been doing in.
Yeah, so in the ones we've been doing, I was saying that we're rotating shapes about the x-axis. When you rotate shapes, the cross-sectional cut, right, the vertical cut, ends up being circles. And that's why in most of the questions, in fact, all of them except this one, it's pi radius squared is how you do it, right?
Mm-hmm.
Well, isn't pi radius squared just the area of a circle?
Mm-hmm.
Now, this shape is different because it's not a rotation about an axis. But the generic formula, right, the general formula that covers every situation is that the volume of a shape is you find the cross-sectional area, right, A of x, and you just integrate that, and that gets you the volume of the solid shape. So you imagine cutting a shape and finding what the area would be at any given point in terms of x. We call that the AX formula. If you integrate the AX formula, you get the volume.
Okay, thanks.
Okay, you're welcome. Okay, who we got for the next one? Anybody want to ask their question?
I just got a real quick one. Can you
Okay.
put up the the formula for the area between two curves reflected over the x-axis?
Oh, rotated.
Yeah, I think you had it up like first thing, and then you took it.
Okay. Around the x-axis, the volume will be the integral from a to b, pi. Essentially, oh, it's the area just between two curves, right? And it's the x-axis. Okay, so that's going to be f of x squared take away g of x squared dx. And that's going to work when you're rotating about the x-axis.
Could we see the piece of paper?
Oh, God.
written?
That would definitely be helpful, wouldn't it? That would be a good idea. So the generic formula for the volume of revolution, which is the difference between two curves starting at A and B. Here's a little picture. This shape being rotated about the x-axis. So it's pi, the top function, which is the big radius squared, take away the second one, which is the little radius squared. Any other question, Trenton? Because that was quite a quick one.
Not really.
Okay, that's good. If you're wanting to leave, feel free. If you want to hang around, feel free. Douglas, what you got for me? Or anything?
Yeah, could I see the first sheet of paper? I wasn't able to finish writing that down.
This guy's here. The one that's important is this one. Pi big radius squared take away small radius squared. I think I may have had another front page as well.
Yeah, I think it was like 1 through 4 where it talked about.
Gotcha. Yeah,
Yeah.
I do have that one as well. I go through a lot of paper. I'll start throwing these away in a moment. Not in that list. I mean, I can recreate it, but it'd be nicer if I didn't have to rewrite it. That would just be an inconvenience. There we go. And that's basically yesterday's stuff. None of the stuff we did today uses these. Although they use the same basic idea, but the difference is it's not the x-axis or the y-axis. It's now going to be a line parallel to the x or the y. So it's better to say big, take away small.
Okay.
Have we got any other questions? If not, I'll get ready for my next class.
Thank you.
Okay. We good, guys?
Thanks.
You're welcome. Bye-bye. Oh, can I use this? Oh, too late. I'll say yes for you.